In this lecture, what we're going to be looking at is flows within, confined flows within fluid mechanics. And so we're going to be looking at the topic that is referred to as being internal viscous flows. So what we'll be looking at, internal viscous flows, these are quite often flows that would be confined within a duct or a pipe or a diffuser. The most popular one within fluid mechanics obviously would be pipe flow, and so we'll spend quite a bit of time analyzing pipe flow and coming up with the equations enabling us to figure out the drop in pressure as fluid flows through a pipe. Before we get to that, what we want to discuss are the two main regimes that a flow can exist in, with any kind of flow that is, but we'll look specifically at pipe flow here. So one of the two main flow regimes that we have is that of laminar flow. Now, laminar flow has the characteristics of the flow being very smooth and orderly, and if you were to look at it, you would not see a lot of change with time. The flow would be moving in a smooth manner. If you had a flow visualization, you'd see all of the flow moving parallel to one another, and consequently that would be a very smooth flow, and that's characterizing laminar flow. The other state that the flow can exist in is turbulent flow. So turbulent flow, counter to laminar, the fluid flow is fluctuating at all times, and so consequently, if you were to put something like a velocity probe within a turbulent flow, you would notice that the velocity would have an average value, so there'd be a mean value, but it would be fluctuating with time about that mean value. And we live in a turbulent boundary layer. The planetary boundary layer of the Earth during the day is obviously very, very turbulent. If you've ever landed at an airport on an aircraft, you'll feel as you come through the cloud layer, as you approach the Earth at about a kilometer up, that's when you start entering a planetary boundary layer and you'll encounter a lot more turbulence. Now at nighttime, sometimes what can happen is that turbulence will all kind of die out, and you get a very, very calm boundary layer that would be at nighttime. However, daily we encounter turbulence. So turbulence is actually the more common flow state that we encounter in engineering applications, at least, but also within nature. And so which state you exist in has a big implication in terms of when we look at internal viscous flow, the pressure drop within a conduit or a pipe. And the state that you exist at is a function of one of the non-dimensional numbers that we looked at when we did dimensional analysis, and that is the Reynolds number. And so what we will do, we'll take a look at the Reynolds number. Okay, so if we were to take a velocity sensor, and there are many, many different ways that you can measure velocity in a fluid, but the one that is often used for being able to study turbulent flows, it's an intrusive sensor, but it's called a hot wire anemometer, and it is capable of measuring high frequency fluctuations in a flow. There are other techniques that have been developed in more recent years, optical based techniques, laser Doppler velocimetry, particle image velocimetry, time-resolved particle image velocimetry. Those are starting to give us the ability to be able to get a time-resolved velocity measurement. But the hot wire is one that's really quite good. It's easy to do. And if you were to put it into a flow, and let's say we had laminar flow regime over here, and way over here on this side would be turbulent. And in the middle is what we call a transitional flow. And in this region, the equations get a little more difficult to come across because sometimes you're laminar, sometimes you're turbulent, you get these turbulent bursts coming out. But if you were to put a sensor, a hot wire anemometer, into a fluid flow and measure the velocity, what you would find for laminar flow is you'd have something like this. Now, it wouldn't be perfectly flat. There'd be some fluctuations there, and that would be associated with the background turbulence that would be in the flow field. There may be some instabilities in the fluid. There may be something driving the flow. You might get a little bit of vibrations off of a pump or a fan. And consequently, it's very, very difficult to get very, very clean flow without any kind of disturbances in it. But anyways, that would be laminar. It would have some average value here. And then if we were to look at transitional, what you'd find is it would be nice and steady, and then once in a while you get these bursts coming up. But they would decay back down, and then you might get another burst and it would decay back down. So the nature of transitional flow is instabilities can arise, but they will damp out with time, and then you return back to the laminar state. And then finally with the turbulent flow regime, again, you do have an average, but the nature of the signal is quite scattered, and it's very, very dynamic. And so a turbulent signal could look something like that. Now, just looking at a signal like that, it's very difficult to determine whether or not it is turbulent. We use a technique called spectral analysis, where we will look at a power spectra of our signal, and by looking at that, there are certain telltale characteristics that we won't go into in this course, but would give you an indication whether or not you do truly have a turbulent flow or if you don't. And then the same with laminar. You can do power spectral analysis on that, and by looking at the power spectra plotted in certain ways versus wave number of the flow. I won't get into details with the wave number, but you would have a certain slope for laminar versus turbulent flow. So that would be what the signal would look like. And but again, with turbulent flow, you are going to have some average values. You do have statistics with turbulent flow that enable you to determine things, and they will be stationary. They don't necessarily change with time unless your flow field is changing with time. So that is laminar and turbulent flows. Now, when we look at duct flows or pipe flows like we're talking about here, so if you were to plot pressure drop in a standard pipe as a function of the velocity of the fluid going through it, what you would find, and if we were to say this here in this part is laminar, and this part here is turbulent, as the velocity increases, so this would be transitional. Now, what you'll find if you were to plot delta P as a function of the velocity, in this section here where it's laminar, we find that delta P is proportional to the velocity. And as we go through transitional, the slope here changes, and then we get a change in slope characteristic. And when we get up into turbulent, we have delta P is proportional to velocity to the 1.75. So what that tells us is that when the flow becomes turbulent, we have a higher pressure drop along the length of the pipe, and consequently it takes more energy to transport a fluid if we have turbulent flow. Now, there was an experiment that was done years and years ago by Osborne Reynolds, and he was doing these experiments, and what he did is he had a pipe, and it was gravity fed, and so it was a very, very smooth pipe, very calm. There was no pumping the fluid that would lead to any kind of disturbances. But he had a very carefully designed bell mouth entry, and he introduced a dye, a laminar dye, into the flow, and he could track that dye. And when the flow was laminar, he would get something that looked like that. And when he would do the experiment by increasing the flow rate, so he would increase the flow rate, which would drive the velocity, the average velocity in the pipe up. And when he would do that, I'll draw this again. So as he increased the flow rate and he went into the turbulent regime, what he would find Again, when he would introduce the dye, it would come in this way, but then it would start going into instabilities, and then it got very, very difficult to see. And so it basically looked like the dye had diffused in the pipe, but actually what it was is there was a turbulent flow. And so if you take a spark photography, you would see the streamlines, and they're very convoluted and very complicated, and that's characteristic of turbulence. If you're looking at the smoke coming up off of a cigarette, for example, you'll notice that it's very nice and smooth and laminar, and then it goes into instabilities and eventually becomes kind of turbulent as it ascends up. Same sort of thing with Reynolds' experiment. Interesting thing is they went back and tried to replicate the experiment, and they found that they could not repeat it with the same Reynolds number in terms of when you would transition from laminar to turbulent. And what I have heard, it goes that the disturbances from modern infrastructure led to disturbances on the side of the experimental facility, which made it harder to get the same Reynolds number that Reynolds originally had, showing that external disturbances can play into the way that experiment goes. But typically what we do for pipe flow, we say that there is a critical Reynolds number, and we always have a critical Reynolds number for any kind of flow that we're looking at. And what that indicates is when the flow will start to transition from laminar to turbulent. But for pipe flow, the number that we use is 2300. And here, RED, that's Reynolds number based on diameter. So Reynolds number is the density of the fluid, the velocity, some characteristic velocity, a characteristic length scale, that being diameter, and then the dynamic viscosity. So in this case, V is equal to an average velocity. And we have to say that because we're going to have a velocity profile. If you look at the velocity in pipe flow, depending if it's laminar or turbulent, it may look like that, or it may look something like that, depending upon what state you're in. And D, little d, is equal to the pipe diameter. Now, quite often you may find in books people saying RE greater than 4,000 is turbulent. Now that's more of a conservative estimate because between 2,300 to 4,000 or 2,100 to 4,000, you could be in the transitional regime. So this would guarantee that you certainly are within the turbulent flow regime. However, I have also heard that experiments can be conducted where you can get Reynolds numbers as high as 10,000. And you still have laminar flow, but I think that would be a very, very specially designed experimental apparatus where you minimize all instabilities, all disturbances, and it would be very, very difficult to replicate anything like that industrially. And so that's more just a scientific type investigation. So for our purposes, typically if you see anything around here, 2,000, 2,100, 2,300, you're starting to go into a turbulent flow scenario, and certainly by the time you get to about 4,000, you can say you have turbulent flow, and that enables you then to determine which equations you need to use to solve for whatever problem you're looking at. So that's Reynolds number, laminar, turbulent flow. What we're going to do now is we're going to continue on looking at pipe flows.